What do you think is the worst, deadliest creatures and endangers human life?
A shark, crocodile, dog, snake, or humans? The answer is the tiny mosquitoes, which kills 725,000 lives a year, and over 400,000 of these deaths are caused by malaria alone.
Salam sejahtera, ladies and gentlemen. I'm Yiling from the Department of Parasitology, Faculty of Medicine, University Malaya. Today's topic is on malaria, with special focus on Plasmodium knowlesi.
A child dies of malaria every 2 minutes, and each year, more than 200 million new cases of the disease are reported. Sub-Saharan Africa is the most affected region, home to 85% of the global malaria burdens. The rest include Latin America regions and Southeast Asia. Yearly, US 6 billion was spent on malaria control and eliminations, and this number will increase to 8.7 billion by 2030. Malaria is a parasitic infection transmitted to humans by the tiny mosquitoes. The life cycles of malaria parasites in humans begins when a female Anopheles mosquito injects parasite into the host while taking a blood meal. Here is a video of the life cycles.
The malaria life cycle is very complex and involving many stages. As the mosquito feeds, malaria parasites enter into the human bloodstream. They quickly move their way into the liver and infect liver cells. With the help of certain sporoid proteins, the parasite develop into schizone, creating tens of thousands of merozoites which burst out the cells and journey back into the bloodstream. They then infecting healthy human red blood cell, reproducing and eventually erupting the cells and rebirthing more merozoites, which in turn go on to infect more red blood cells, leading to the massive destruction of red blood cells. A few of the infected cells develop into chamatocytes, which can remain in the bloodstream for several days and may be ingested by another mosquito during the subsequent feeding. Inside the mosquito, the chamatocytes develop into new sporozoites. So now the human has infected the mosquito, the life cycles come to full circle and continues.
There are about 20 different Anopheles species. They start biting by late evening and peak at midnight and early morning. Shallow freshwater such as puddles, rice fields, and hoof springs are the breeding sites for egg layings. In Malaysia, forests are the hotbeds of malaria as they provide the conditions that are conducive to the survival of the malaria vector. Following the infective bite by the mosquito, a period of time goes by before the first symptoms appear. Malaria causes flu-like symptoms such as fever, headache, dry cough, chill and sweats, abdominal pains, vomiting, and muscle pains, which could eventually develop into severe vomiting, coma, and even death if untreated. Humans are the natural host of 4 main species of Plasmodium. Plasmodium falciparum, which is the most prevalent species in Africa regions. Plasmodium vivax is in Southeast Asia and India. Plasmodium malariae and ovale are less prevalent and produce mild symptoms. Other than human malaria, there are over 150 species of Plasmodium have been described to date, infecting other mammals, birds, and reptiles. Despite having such a large number of hosts, in general, malaria parasites tend to be host-specific. However, it is not the case for Plasmodium knowlesi. Plasmodium knowlesi is a malaria parasite found naturally in bender leaf macaques, long-tailed and pigtail macaques in the tropical forests of Malaysia and elsewhere in Southeast Asia. The life cycle continues in the monkeys through the Anopheles mosquitoes, and humans become infected when these mosquitoes bite the humans. Thus far, several mosquito species belonging to the leucovirus groups have been incriminated as vector for Knowlesi malaria, as listed here. Let us take a few minutes to appreciate the history of Knowlesi.
Plasmodium knowlesi was first described by an Italian physician involved in a study of tropical medicine in 1927. It was first isolated and studied in detail in the Kolkata School of Tropical Medicine in India in early 1931 from a long-tailed macaque that had been imported from Singapore by Campbell. Knowing that malaria was the research focus of Knowlesi and Dasgupta, he then handed the macaque to them for a series of experiments among its natural hosts. In 1932, Knowlesi and Dasgupta successfully infected 3 human volunteers with Knowlesi malaria. Between 1935 to 1955, P. knowlesi would go on to be used as a generic parasitic agent for various diseases, particularly neurosyphilis. The first case of natural infection in a human was only reported 34 years later when an US Army surveyor acquired the infection while working in the forest in the state of Pahang in peninsular Malaysia. This single case was followed by a presumptive human case of Knowlesi malaria that was acquired in Johor in 1971. The general health view that zoonotic malaria was an extremely rare event changed following the discovery of a large focus of human infection with P. knowlesi in the Kapit division of Sarawak in 2004.
What happened in 2004? The infections in Kapit were initially misdiagnosed by routine microscopy of blood films as being caused by Plasmodium malariae. While Plasmodium malariae infections are usually benign, some of these patients were having severe malaria. The subsequent retrospective studies using Plasmodium knowlesi specific primers for PCR and DNA sequencing identified 58% of these patients were infected with Plasmodium knowlesi. Instead, they were misdiagnosed as P. malariae initially because Plasmodium knowlesi and Plasmodium malariae are morphologically very similar under microscopy. Human Plasmodium knowlesi infections were subsequently demonstrated in other states in peninsular Malaysia and Malaysian Borneo by this species-specific nested PCR. Since then, human Knowlesi malaria cases have been reported in most of other countries in Southeast Asia. Today, Knowlesi cases are mostly reported from individuals who have history to forest environments where the monkeys reside. On top of that, the vectors that can transmit Knowlesi are mainly the forest feeders. With the extensive human population growth of the last decades, humans encroach closer into the natural habitats by activities such as deforestation. In response, non-human primates move towards the forest fringe and mosquito vectors are increasingly found in human habitats. All these changes may facilitate the emergence of Knowlesi malaria. Hypotheses such as loss of relative immunity due to low rate of other malaria could be one of the reasons. Increased sensitivity of the diagnostic methods, such as the use of nested PCR, has also played a role. For a better understanding of the risk factor and predicting the future outbreaks, mathematical modeling can be applied. These kind of studies are currently ongoing in our lab, and hopefully by modeling, it will lead to better understanding of the disease natures for Knowlesi malaria and forecasting the future outbreak and evaluating potential interventions. Symptoms of acute Knowlesi infections are similar to those seen in all malaria, but P. knowlesi has the shortest life cycles among all human malaria, approximately 24 hours, while other species' life cycles are between 48 to 72 hours. Therefore, in Knowlesi infections, if untreated, the parasite will continue to grow rapidly which could lead to severe malaria, which can cause thrombocytopenia, renal failure, hypotension, jaundice, and acute respiratory distress. Some require a prolonged periods of care in the intensive units, with some of them die of complications.
The good news is malaria is treatable and preventable.
Treatment for malaria should be initiated as soon as possible. Drug regimen to treat malaria depends on the clinical status of the patients, the species of the parasites, the area where the infection was acquired, and its drug-resistant status. In Malaysia, uncomplicated malaria is usually treated by artemisinin-based combination therapies, primates. Primaquine is usually used for malaria species that are potentially relapsed, such as Anopheles and vivax malaria. For severe malaria, artesunate will be administered, usually by IV plus oral doxycyclines. For countries without drug resistance, quinine and chloroquine can still be used.
Insecticide-treated mosquito nets are widely used to prevent malaria transmission. Sleeping under the net can reduce the contact between the mosquito and humans, and the insecticide can kill the mosquito once it is in contact. Indoor residue spray involves spraying the inside of the house structure with an insecticide with long residue additives, typically once or twice a year. Anti-malaria drugs can be used to prevent malaria. For travelers, malaria can be prevented through chemoprophylaxis. Rapid diagnosis is essential for immediate treatment of malaria. Education and create awareness of preventing malaria are equally important. Ultimately, a malaria vaccine is needed. A malaria vaccine RTSS was launched in April 2019 in Ghana as Phase 3 clinical trial. However, the effectiveness of this vaccine has not been tested against Knowlesi malaria.
Therefore, vaccine development targeted at P. knowlesi is still needed. Development of an effective vaccine has focused on selecting antigens that can provide long protections and block the invasions of red blood cells. Studies have shown that parasite antigens, which are recognized by the host immune system, accumulate polymorphisms to evade host defense mechanism and are the prime targets for the vaccine developments. In our lab, these are achieved by studying the P. knowlesi antigen natural selections and the patterns of diversity of isolate from Peninsular Malaysia versus Borneo and within humans and macaque hosts. Plastic antigens such as MSP1 and 3, Taffy binding proteins, apical membrane antigens run through spara are the potential targeting antigens, and some of these have shown to be important targets for vaccine studies. This study is currently ongoing, led by Professor Fongmanyi and the rest of the investigators in our labs. Let's take a look into malaria diagnosis. An accurate and early diagnosis of malaria is crucial, especially in Knowlesi malaria. Microscopy is still the gold standard for malaria diagnosis. It is widely used, especially in rural settings, and it is very economic and it is reliable for diagnosis of the 4 conventional human malaria species. However, it is not possible to accurately identify P. knowlesi by microscopy, since the morphological features of the early trophozoites of P. knowlesi are identical to those of P. falciparum, with double chromatin dots and no enlargement of infected red blood cells. The rest of the blood stage of P. knowlesi resemble those of P. malariae, including the diagnostic features of band-formed trophozoites. Since P. knowlesi parasitemia increase very fast and causes more severe disease than P. malaria, so it is very important to identify and treat the infection quickly. Rapid immunochromatodiagnostic tests have also been developed for detections of Plasmodium species and very useful for lab technicians who are not familiar with microscopy detections.
The RTTs contain antibodies that are specific for either falciparums or vivax or pan-malaria species. All the current commercially available RTTs were developed long before Plasmodium knowlesi was discovered. Therefore, these RTTs were not optimized for detections of P. knowlesi and could detect P. knowlesi as P. falciparums, P. vivax, or other malaria species. In our labs, our students have been actively exploring alternative antigen candidates that can be employed for the specific detection of PK, including MSV, SPR, and also CSP proteins. Over the years, many molecular methods have also been developed for diagnosis of malaria. Microscopy and RTT share the similar disadvantage, which is insufficiently sensitive for detections of low parasitemia and asymptomatic infections. Therefore, diagnostics tools with better sensitivity are required. Molecular detection methods have consistently proven to be more sensitive and specific than these two methods, with detection limits as low as 1 parasite. Nasal PCR is the most commonly used molecular test so far for malaria diagnosis. This method has been described for knowlesi, including those targeted as SSU RNA genes, THFR, CytoB, and CSB genes. Although nasal PCR can specifically detect P. knowlesi infections with high sensitivity, there are disadvantages. This method is costly as it requires expensive equipment and reagents. On top of that, the turnaround time to perform nasal PCR also very long, which requires 6 hours, which is too long for rapid diagnosis. Affordable and rapid tests with adequate sensitivity and specificity for knowlesi is much needed. Recently, we have found a new method, which is LAM, which can be overcome all these challenges.
Loop-mediated isothermal amplification assay, in short LAM, is a rapid and cost-effective molecular diagnostic method. LAM is highly specific as it employs a total of 6 primers, recognizing 8 distinct sites of a target region. A strand-displacing DNA polymerase called PST polymerase is used for DNA synthesis to bypass the need for 3 temperature cycle conditions as seen in a normal PCR. LAM can amplify DNA to million copies in less than an hour under a single temperature.
PST polymerase work best between 60 to 65 degrees, so to run a LAM test, a simple incubator that can maintain the temperature at 65 degrees is sufficient to perform the test. A PCR machine is not needed. Therefore, it makes it very affordable. On top of that, the amplification can be completed within an hour. The sensitivity and specificity of LAM has also been shown to be equivalent to PCR, if not better. In 2011, we published a paper on using LAM for specific detection of P. knowlesi. Subsequently, this method was improved to detect all human Plasmodium species. It has shown to be 100% specific and sensitive for detections of all human malaria species, and the whole process can be performed in 35 minutes. Because LAM is rapid, sensitive, specific, simple, and affordable, we have a strong belief that it can be used as a point-of-care test to be performed at the time and place of the patient care. In order to do so, we use LAM tests directly on finger prick blood without going through DNA extraction using commercial kits to save costs and times. With these optimizations, the whole test can be performed in less than 1 hour, and the test result can be observed by looking at the color changes after addition of color dye, or loading onto the lateral flow device by looking at the band. And in the lab with real-time PCR machines, it can also be observed by looking at the peaks. This part of the study is still ongoing. In our lab, Lamb test has also been developed for toxoplasmosis, leptospirosis, dengue, Shigella species infections, and most recently, Lamb test has been used for diagnosis of COVID-19. The next question is malaria elimination within reach? When a country has zero locally acquired malaria cases for at least 3 consecutive years, it can be certified malaria-free by WHO.
Malaria eliminations is the goal of many countries in Southeast Asia and Western Pacific, and large reductions in malaria prevalence have been achieved. Globally, the elimination network is widening and more countries moving towards the goal of zero malaria. This is a strong indication that malaria elimination is within reach. According to UN and Bill Melinda Gates Foundations, the world could be free of malaria by 2040. But our journey is far from over. Resistance to anti-malaria drugs is not new. Resistance of falciparum to chloroquine and sulfadoxine pyrimethamines became widespread in 1950s and 1960s. Recently, artemisinin resistance is prevalent in the Greater Mekong sub-region.
The drug-resistant malaria in Great Mekong is strengthening the malaria elimination. If drug resistance expands to Africa, where the malaria rate is highest, we could see the massive resurgence in death. So, how could we stop resistant malaria? By strengthening the surveillance system to find every malaria cases, by ensuring every case is correctly diagnosed by microscope and rapid tests and immediately treated, by educating, protecting, and treating all communities, including mobile and migrant populations, by combating poor quality, counterfeit, and fake drugs, and by investing in new drugs to treat malaria. We need politicians, donors, NGOs, and citizens to work together to eliminate the disease.
Another problem that has stalled the fight against malaria is insecticide resistance. Only a handful of insecticides are officially recommended for adult mosquito control, and over the years, continual use of some insecticides have enabled the highly adaptable mosquito to develop significant levels of resistance. One key approach is to develop and safely apply insecticides to which mosquitoes haven't acquired resistance. The research work to find new mosquito insecticides should continue. Last but not least, zoonosis can compromise malaria control efforts. The interruption of its transmission is challenging and may not be achievable in areas of high forest coverage. In Malaysia, since the malaria eradication program was implemented in 1967, total malaria cases decreased dramatically. However, Knowlesi notification increased yearly since its discovery in 2004. After 10 years in 2014, human Knowlesi infections have been dominating the infectious rates of other species. Malaysia is aiming to eliminate malaria by 2020. Since 2018, we reported 0 indigenous malaria cases. However, these figures refers exclusively to the human-only Plasmodium species. The actual number of malaria cases in 2018 was 4,630, and Knowlesi accounted for 89% of the total. Knowlesi is currently the most common cause of malaria in Malaysia and is associated with the highest risk of severe disease. More worrying is Plasmodium Knowlesi can travel too. There have been several reports of imported Knowlesi cases all over the world, including USA, Germany, Spain, France, Japan, and many more. According to Science News, Malaysia could be the ground zero for a new global malaria threat. I'm sure this has been recognized by our local health authorities responsible by malaria control by now. Increased investments, innovations, and collaborations will require in order to develop a more integrated efforts to control zoonotic malaria. Human Knowlesi malaria was discovered in Malaysia. It is my hope that it will end here too. We may not be able to eliminate the zoonosis, but we should be the one that control it. It is a war between human and the mosquitoes. Are you ready for it? All you need to do is to speak up.
If your voice could change the course of history, would you speak up?
If your voice could set people free.
If your voice could empower millions.
If your voice could open minds and inspire the world.
Would you speak up?
If your voice could save a life.
What if it could save millions of lives?
Would you speak up?
Malaria is our oldest and deadliest enemy.
It is thought to have claimed the lives of 54 billion people.
That's the current population of the world.
Wiped out 7 times over.
Next year, almost 500,000 more will be added to that number.
We can end this.
Sign our voice petition, and together
We can end malaria for good.
It's time to speak up.
it's time to speak up.
It's time to speak up.
With your voice, we can be the generation to end this forever.